Okay, so let's begin. Okay, good morning. Welcome to Deep Learning in Computer Vision. Today we're going to talk about object detection and image segmentation. So we're going back to some basic tasks. So let's recap on what we learned so far about deep learning in a supervised settings. So in order to do supervised learning, we need 4 components. We need data. So we need training data with labels. So the inputs are X, the output we expect to get are Y. Someone annotated images for us. We have some model. It's a deep neural network that operates on X and predicts Y. And we need a loss function, a criterion that matches between the predicted Ys and the ground truth, the labeled ones. And then we have an optimization stage where we find the parameters of the model such that the predictions matches the annotations as best as possible. Okay? And of course, in deep learning, the model we're using is a deep neural network. Now, so far we've discussed image classification as a supervised task, but we can think about additional tasks such as object detection, where we have several objects in the image and we want to output what objects are in the image and where they are. So we want to annotate the object with bounding boxes that specify their exact location in the image. We can think about semantic segmentation, where we want the annotation to be very precise. What pixels belong to which object? But in this case, we have semantic segmentation and instance segmentation, and they are not exactly the same task. So in semantic segmentation, we want to provide semantic information for each pixel. So it's like a classification task per pixel. So we want to annotate all the cat pixels as cat. But the fact that we have 2 cats in that image will not be reflected in the result of semantic segmentation because it only cares about differentiating between cat pixels and dog pixels. Instance segmentation takes this task one step further and actually says, I want to separate between instances even if they are of the same class. So I want to know that these pixels are cat pixels, but I want to know that these pixels belong to a different instance of a cat than this one. Okay, so we're going to discuss these 3 tasks today. So in order to perform tasks, we need data. So for image classification, we usually work with ImageNet, which is 1 million images annotated with 1 label per image. What is the dominant class in that image? For detection and segmentation, we have additional data sets. Usually people work with this data set, which is called MS-COCO, Microsoft Common Objects in Context. It has 200,000 images, 1.5 million instances marked in those images, and they have 80 object categories annotated in the dataset. So is 200,000 images less than the 1 million images of ImageNet?
More information per image, right?
That's correct. So we have less images, but we have more information. We have richer annotations. So it is possible to train very complicated models on this data.
These things, is it someone that sat and annotated all of the images, or is it us when we do captchas in Google and stuff like this?
So I don't know if they do it automatically with captchas, but I'm certain it's not a single person. Usually use mechanical Turks and these kind of annotation services. So there are services where you pay people very low sums of money and you get some annotations.
So with these people just in third world countries instead of like Microsoft Office?
I guess so. Yes, I don't think they pay their engineers to annotate images. I don't know, but it's a guess. there are works that try to game this thing, so like using captchas and things like that to get better annotations. But usually when you have a large data set, you don't have time and you pay for annotations. And there are companies that this is their business model, provide annotators, even expert annotators for some domains. But yes, annotation is a serious bottleneck, and this should motivate the lectures you've heard about self-supervised learning, where you want to avoid as much as possible the hurdle of annotation. So if you have a trained model in a self-supervised manner, you might not require hundreds of thousands of images and millions of annotations. You might be able to perform tasks, even segmentation detection, with very few number of annotations. But that's beyond the scope. So let's talk about object detection. So we have an image. This image might have more than one object in it, and we want to say, where are the objects and what are they? So what are the challenges in this task? So why not just do image classification? What's the difference? Yes.
Classification on what? If you're gonna have like a million different boxes, you can do classification on.
Okay, so we don't know in advance the number of objects. That's one. And another is that we have multiple types of output. So we don't only predict probability of a class, like in classification, we also need to predict the bounding boxes. So we need to predict two different things per object, and we don't know how many objects there are for each image. It changes between the images. Also, when we want to do object detection, we usually want to work with more detailed images. So in classification, we usually reduce the resolution of images and work with 200 by 200 something pixels. In object detection, we usually want to work with larger images so we can spot finer details and smaller objects. So we have resolution on top of these two challenges. So let's take it one step at a time. Let's consider for a second that there's only one object in the image. We will deal with the multiple objects in a few slides. But now let's deal with the fact that we need to predict two things. We need to predict the class and the location. So let's think about this localization task where we have a single object in the image. We want to classify it like we did before, but we also want to localize it. So we want to provide a tight bounding box around the object. So for classification, we have a deep neural network, a backbone, and it outputs a feature X, and we can project, we have a linear layer that projects these features and classify them into one of the 1,000 classes we have. This is image classification. And we train this with cross-entropy loss. So we have a label, a discrete label cat. We predict some probability over all the classes, and we have cross-entropy loss. And we propagate gradient to the network. But if we want to predict the position of the object, we don't need to train a new neural network to do that. We can use the same backbone, the same features, because they already know something about the image. So what we can do is we can take the same output features and predict 4 values, which are the corners or the center and the size of the bounding box. So a bounding box requires 4 parameters. We'll predict them. And then we can have regression loss, like an L1 loss on these predictions. So classes are discrete, so we have cross-entropy loss. bounding box is continuous, it's regression, so we have a different loss. Okay, so we are sharing the features, and we predict the two types of predictions we need to predict from the shared features. And we use different loss function according to the predictions we are trying to make. What are we doing with two loss values? So when we learned about backpropagation, we used a derivative of the loss with respect to all the parameters, but we are talking about a scalar function. So we need to combine these losses. So we need somehow to have a weight between the two of them. And if you come from physics, then you know that you can't just take cross entropy which measures bits with L1 loss that measure pixels and put them together. So this lambda actually needs to convert between pixels and bits. But usually you just put a number there. And now that we have a scalar loss, we can take the derivative with respect to this joint loss, which is a weighted sum of the two loss terms that we have. So the derivative of the cross entropy component with respect to the parameters of the bounding box prediction is 0, because this layer doesn't affect the prediction of the class. So it's 0. And in the same way, the derivative of the L1 component of the loss with respect to the classification head is also 0. But once we are propagating into the backbone, both the components are relevant. And because of the chain rule, we don't need to explicitly define how these gradients are affecting all the backbone. It is simply the weighted sum of the gradients. So we are having two loss functions over the two predictions we are making. Each loss function will affect the head that predicts the relevant output, but both of them will affect all the features that we are using. So we're going to get features that are trained both for classification and for localization of the object. Okay? Okay.
Might say 4 power.
It's not 4 to the power of x, it's w something times x. So x is the features, and we have this weight function, this weight matrix that project the features x from dimension f, whatever dimension the backbone outputs, to 4. So we need to predict 4 variables. So it's x times w in that case. Oh, no, it's transpose. Okay. It's okay. All right. Great. Okay. So we know how to train a network that would produce different outputs, both classification and localization. And now we're going to deal with the second challenge of predicting variable number of bounding boxes for an image. So the most naive way of doing this is, suppose we have this kind of trained localization network. Someone trained it for us. We can simply run it on the sliding window over all the image and try to localize objects within a sliding window. So we have some fixed size, and we slide it over the image, and we try to classify all the crops of the image and localize the objects inside. So if we have many objects, we are going to slide the window. And we can do it even with different sizes of sliding window into account for different scales and different aspect ratios of the objects. And then we can classify and localize in all these regions. But what are we going to get? So we are going to get some windows that looks like this. So what is going to be the prediction of this localization network for these windows? So we're going to localize the cat here. We're going to localize the second cat and the duck, and we're going to predict them. Maybe we didn't choose a window large enough to capture the entire dog, but the localization network can generalize a bit. So if it sees only part of the object, it doesn't necessarily have to predict the bounding boxes within the image. It can also predict something outside. So if the window captures a significant portion of the dog, even not the entire, it can still predict the bounding box, what is the expected boundaries of the dog, and output the class correctly. So this can still work. But if you're sliding the window over the entire image, most of the crops we're going to get are going to be something like this. So what should we predict in this case? And suppose the bucket is not part of our labels that we want to predict. So what is the prediction should be in that case?
Grass.
Grass is not part of our label set. So yes, we have, suppose we only have animals in the label set. Yeah.
I mean, you could maybe say that it should still predict that because the amount of fixes you have for a cat here is similar to the second cat. So, but on the other hand, you're also missing like very key components of the cat.
Yes.
So
And there's a confidence level that you have. You might get a chance, but the confidence level will be very low. Great.
Yes. So in that case, what you really want to predict is to say, well, there's nothing here. Yes. So we are going to add an additional class to our prediction, which is background. There's nothing here. Drop this this crop. So we have two prediction heads for the network. One that predicts classes. So it predicts a new class background. What would be the prediction of the bounding box for this case? We don't care about the bounding box. So it can predict whatever it wants. It's a function. It will compute some numbers, but we don't really care. So if we predicted background, then we don't care what is the prediction of the bounding box. Yes.
do we care though if it's like overlapping with an object? Like in this case, it's overlapping with the cat's so when we want to say like as long as it's not going into the bounding box of an object, it's okay.
Well, since we're running in a sliding window, so if we have a portion of the cat here, we most likely have other windows that have significant overlap.
So,
And then we want to see their prediction because we are more confident, we have more information there, they are more likely to predict better. In this case, don't even try. Yeah, question? No? Okay. So if we have a localization network that was trained to predict classes and bounding boxes, we can run it on in a sliding window on the entire image. We can even run in different scales of windows to account for shapes, and we'll have localization and classification where we are overlapping significantly with objects, and many windows will be just classified as background, and we can discard them. So the network will try to predict a lot of windows and will only leave the very confident ones that actually contains objects. So this is how we can deal with the varying number of objects in an image. Are we done? Have we solved object detection? Almost. How many overlapping images, overlapping windows there are in a reasonably sized image? Well, if you have a large enough, so we handled the multiple type of object, we handled the varying number of outputs, but we're not done because actually, if the image is reasonably sized, 600 by 800, and we consider large windows of 200 by 200, for example, there's still hundreds of thousands of possible overlapping sliding windows in an image. And if we want to run this network on them, performing inference on a single image is going to take like a pass on ImageNet. So it doesn't make any sense. And if you want to consider different sizes and different aspect ratios of the sliding window, the number even increases. So this is not feasible. So theoretically we can do this, but it's not practical. So, and we want to do object detection in a practical manner. Think about autonomous car. You have a video streaming in, and you want to detect pedestrian cars. This is by no means something you can work with. So this is version 0. Let's do something that makes sense. The key component here was operating in a sliding window on an image and taking all these windows one by one and applying the network on them is not very efficient. Have we learned something in this course about an efficient way of processing something in a sliding window manner? Convolutions, yes. So if our backbone is a convolutional neural network, then we can turn this sliding window operator into a fully convolutional neural network. So instead of these fully connected layers that project the features into classification and bounding box prediction, we can replace them with a one-by-one convolution. And now we're going to compute all the features together with a convolutional backbone. And for each feature, we're going to apply these prediction heads for each feature independently. And
why a one-by-one convolution?
What?
Why is it a one-by-one convolution?
Because we had a feature at the top of the backbone, and we use the fully connected layer linear to project it. And it's equivalent mathematically to applying one-by-one convolution on the feature space. So if we had a crop and the backbone output a single feature in RF, and then we have a matrix W from F to D for 4, for example, for predicting the positions. So we take a single vector and we get a 4 vector for the bounding box. But now if we have an image and we apply a convolutional backbone, this is not a bounding box. Now the feature is going to be some F by H by W. So width and height might be smaller than the width and height of the image because we do striding. But now for each and every one of these features, we want to apply this W. So we convert it to one-by-one convolution that operates on each and every one of these features and produce this 4 vector. Okay? So instead of cropping each individual crop, we just slide everything and we share a lot of the computation due to the efficient way of the way convolutions are implemented. Okay. So now that we turned our system, our localization network into a fully convolutional one, we can simply slide it very efficiently. We don't need to crop, explicitly crop different crops. We can slide it over the entire image. What is the crop size of the system now, of our detector?
How big I'm sorry, forget the technical term, the field of view.
Receptive field, yes, correct. So a backbone has a receptive field, which means that what is the area in the image that affects the prediction? And this is effectively, this is the crop size the backbone works with. Okay? So
What's related to the size of the convolutional and the size of the filter?
So the receptive field depends on the size of the filters and the networks. We went over this, I think, in the 4th lecture, but if you have only one layer of a 3x3, this is the image, then the receptive field here is 3, because the output edge feature at the output is affected by 3x3 pixels. So
Does the other marker work better?
it's so if we have 3x3, then the receptive field is 3x3. Now, if we have an additional 3x3 layer, now each pixel here is affected by 3x3 here, but each one here is affected by 3. So here it's 5x5. Because
Actually, each layer in the network represents a different size of
yes, of receptive field. The receptive field
this is the scaling of
the receptive field grows as you go deeper. If you do striding, then it really increases, it multiplies the size of the receptive field. If you do attention, then your receptive field is the entire image, because you attend each query attend to all the keys in the image. So, and you can slide a transformer as well, but this lecture was intended to be before transformers, but it's still relevant. But there is a way of computing the receptive field. You can Google it, receptive field arithmetics. There's a very nice blog post, I don't remember by who, with nice illustrations and animations that helps you see the way it grows. And you usually don't think about it because you have a network and you apply it and it works. But sometimes it's worth thinking about, like, what is roughly the size of the receptive field. So if you are trying to look for very tiny objects in an image, it doesn't make sense to use a backbone with a huge receptive field. If you're only caring about very large objects, then working with something that is very small also doesn't make sense. So usually you don't need to know the precise size of the receptive field, but you need to know, like, ballpark where you are. And I think for ResNet, it's around 400 pixels, give or take. So this is usually what we're working. So we don't need to crop different windows. We can use the efficiency of convolutions to slide over the entire image. The size of the crop is the size of the receptive field of the backbone we are using. But what if we want to use different sizes of crops? If we want to find both large objects and small ones using the same backbone? And what if we want to account for different aspect ratios of objects? So if we have cars and we have trees, and we want to use the same backbone to track them.
Could you just pick a layer, an intermediate layer from the backbone, or is
But then the features are different, so you need to train these kind of heads, this kind of heads for different layers. This is it was done. There are architectures that are doing this, but not ideally. So yes, this is very efficient. Okay. So at this point, there's like a split in the road when you consider object detection. There's one line that goes with a single shot detection, one pass in the network, and we want to predict all objects, all aspect ratios, all sizes, and do it in a single shot. So this is YOLO, you only look once, and YOLO, I bet you know, has many versions. There's SSD, single shot detector. And we're not going to go this path. There's also a path with two shots. So we're going to take one pass in the network that will give us roughly where are objects and what are their sizes. And then we are going to try to focus on these regions. So this is two shot because we are going to process each region roughly twice. And as you can guess, single shot is much faster because it's a single shot, but it has high false positive. Usually they suffer from relatively higher false positive rate. Again, this problem is very well studied and performance I'm not following, but they are very, very good. And on the other hand, two shots is slower but more accurate because we pay more attention to the predictions we are making. And we are not going to discuss the single shot in this class. I think you'll see YOLO in the tutorial, and I hope so. So we're going to focus on the two-shot approach. So we're going to cover the work that is called faster-RCNN, and you can guess there was RCNN, there was fast-RCNN, and now we're going to do faster-RCNN. So we're going to apply a backbone, a convolutional backbone to the image. We're going to extract some feature. This is a representation of the feature space. And we're going to do this only once because the features are informative and we're going to reuse them for all the objects in the image. So there's no need to crop regions in the image and extract features again and again. So convolution, this is done very efficiently. This is like a single forward pass in a network. This is great. In terms of sizes, so we have 3 channels in the input image, R, G, and B, by H by W, that can be very large. And after processing, we have higher dimensional feature space. So D can be 500, can be 1000, something like this. But the spatial dimensions are going to be smaller, usually significantly smaller, 16 times or even 30 times smaller than the original image. So we pay in resolution and we get more information in high dimensional rich semantic features. So the first stage we're going to do is we're going to propose regions that are of interest. So this is going to be the RPN, the region proposal network. And it's going to operate on the features. So looking at the features, This is a very small convolutional neural network, 2-3 layers, that is going to propose regions of interest. It predicts bounding boxes. It outputs the corners of the bounding box, and it's going to locate where roughly in the image we should look. So some of these regions are going to overlap. Some of them might be off, but it should filter most of these sliding windows that we considered earlier. So instead of hundreds of thousands of possible windows with different sizes and aspect ratios, we're going to be left with only around 1,000, which is a significant decrease. Once we have these windows proposal in the image space, we can find their corresponding positions in the feature space. So if we know how to compute receptive field, we can relate each pixel in feature space to the image space by shift and scale. So if we have a crop in the image, we know what features correspond to this region. And now we can crop these features from the feature space. So we don't need to recompute the features. We already have them. And once we have the features for this region, we can apply very thin classification and bounding box regression for each and every one of these crops. And we can do this for all the crops in the image that were proposed by the region proposal network. And whoops, we get a prediction. So the region proposal network is the first stage. And then once we have these crops, we apply this localization and classification on top of them. This is the second stage. So this is inference. Yes.
Can I have many boxes in the same frame?
Yes. So the RPN actually considers hundreds of thousands of different boxes, and it only passes 1,000, so a dramatic decrease for the second stage. So it's
like a limit over the number of boxes that is taken.
I don't think there's an actual limit, but in practice, because the RPN predicts probabilities, it actually manages to discard the majority of the boxes that clearly are not relevant for the object detection.
Each feature map correlate to a bounding box?
So the feature map is one. We only compute it once with the backbone. So it's squished here, but it's usually the backbone is the very heavy component. It has a lot of layers, a lot of parameters. So taking an image from 3 vector space RGB to this high dimensional rich space, it takes heavy lifting. The RPN and this the second stage are very lightweighted, are 2 or 3 layers.
The RPN is receiving
the features.
Yeah, they're H by W by D, you said?
Yes, and it runs in a convolutional manner on that, and it is being able to propose the different crops in the image.
So there's no relationship to D with the amount of bounding boxes out there?
No. The relation is with respect to the size of because it works in a convolutional manner. It has number of, so we'll see that in a second. So, okay, so how the region proposal network works. So we have an image, we have the feature map, okay? And now for each feature in the feature map, for each position, the region proposal network actually considers several possible bounding boxes. So around each position, it considers different anchors. So fixed, the anchors are fixed on the parameters of the network that was trained. And an anchor says around the center of this specific pixel, we are going to consider these sizes and these aspect ratios. So we might have square, elongated rectangle, and portrait one. And in 3 different scales, so we have 9 anchors, we can have some more. And then for each of these anchors, the RPN will say, do we have an object that roughly aligns with that specific anchor? So this is how this enables the RPN to propose several boxes in different sizes and different aspect ratios around each point in the image. So it has a small receptive field over the feature space, but the features themselves already have very large receptive field because they are the result of a very large bounding box. We have a very thin layer here of a convolution, and then it predicts the refinement for the anchor and whether it's an object or not. Should we consider this or not?
The backbone is the same one as for classification, or it's specific for object detection?
So usually reuse. So in RCNN, they took, I think, VGG, which was pre-trained for classification, and then they fine-tune it for object detection. In more recent papers, I guess they trained from scratch or reuse self-supervised backbones. But usually you prefer to use some trained backbone to start with. It gives you a good initialization and then you refine.
But you have to refine the backbone itself for object detection?
Yes. So you train everything. It's
So how many bounding boxes it create?
so it considers the number of anchors you have. So if you have,
How many?
so you decide on the number of anchors when you design the system.
Okay. So have a maximum potential bounding boxes for each anchor.
So so suppose you have 9 anchors. So you have these 3 squares and you have 3 scales. So you can consider a very large square around the point and smaller and smaller. So you have overall 9 anchors. So, and then you have a feature space, which is d-dimensional by h by w. So overall, you have 9 times h times w possible bounding boxes. Okay, which can be a very large number. So these are the anchors that we have, and we want to enable the RPN to refine the anchors. So if you have a very large bounding box, you want to be able to shift it a bit, and so that you can crop more accurately the features for the second stage. So if we have an anchor that is parameterized by the center position and the size, the width and height, and we want to predict an object that is most relevant for this anchor, so we want to predict the green bounding box where we have the blue anchor. So we want to be able to refine it. So what we are predicting for each and every one of the anchors, we are predicting a correction in the position of the center of the bounding box and the scale that we want to output. And we predict the position relative to the scale of the anchor. So if we have a very large bounding box, we allowed it to shift more. If we have a very small one, we don't want it to move far away because we expect the next feature maybe to catch this small object better. And when we predict scale, we predict it in a log space because if we are around a very small object, we care a lot about the accuracy. If the object is very large, if you are off by 1 or 2 pixels, it's not very critical. So for each anchor, the RPN predicts a correction with respect to the ground truth boxes in the object. And if we have this predicted correction, it's very easy to predict the correct bounding box. So how do we train the RPN? So we have an image and we have a bounding box annotation. So in classification, it's very easy to train. We have an image, we have a class, and for each image, we need to predict one vector of class probability, and we can match this with the annotation we have. But now we have an image. The RPN is going to predict a lot of anchors, and we only have one bounding box annotated on that image. So how are we going to match this annotated bounding box with all these predictions? So we are going to predict all these proposals, and we are going to match between the predicted proposals and the ground truth annotation we have. So if the ground truth bounding box overlaps significantly with the proposal with an anchor, then we consider this as a positive supervision, and we're going to supervise this anchor with this specific annotated bounding box. And what is this intersection over union? So we have the anchor and we have the annotated object. This is the union of their area. This is the intersection. And we are going to measure the intersection over union. So the intersection over union ranges between 1 when they perfectly overlap and 0 when they don't have any overlap at all. And 0.7 is a significant overlap. 0.9 is almost perfect. If the intersection over union of the annotated bounding box and some anchor is less than 0.3, which means this is a significant, they don't overlap well, then the supervision for that anchor is going to be negative. So this anchor should predict background. Okay? And then at inference, we can discard this anchor. We can discard this proposal. If it's in between, then we don't want to apply supervision during training. So we make a prediction and we don't compute gradients for these predictions. We just ignore them because they are somewhere in the middle. Maybe they might be able to produce good objects in inference. Maybe they are not very good. So we don't want to train these. So we want to focus on those that we have confidence that they can produce good proposal. We want these one to give us confident predictions. There's nothing here, don't bother with these regions. And we ignore the rest. And the loss that we have. So we have two terms, one for the bounding box, for the refinement of the bounding box, and one, the classification. So the classification is if we positive or negative. So this is loss over all the proposals that are either positive or negative. Again, these are ignored. And the refinement loss is only applied for the positive bounding boxes. Okay? Great. So this is training. So during training, we have this step of assignment between predictions and annotations. It's a step that didn't exist in classification because it was trivial. But now we need to do this. And once we have the assignment, we know the supervision for each and one of these, for almost all these predictions. Questions?
How is this different? Like this, I know you said you wouldn't explain the YOLO and the other ones, but how is this doing it twice?
So in YOLO, and they actually concluded this step. So they trained this to predict not only for object or non-object, but all the classes. But again, you consider a lot of proposals here, so you are prone to a lot of false positives during inference. In two-stage, we are going over the proposed regions a second time. And the second stage can also deem regions as background.
May I ask a question?
Yes.
Yes. To me, it sounds maybe very complicated. Wouldn't it be simpler to work on a pixel base, whether this pixel belongs to this to the cat or to the dog or whatever, and then just make a bounding box over all the pixels that belong to the dog, for instance?
And we will touch upon this on pixel segmentation in the next part of the lecture, but we need to move on. Idan, I hope your answer will be answered after the second part.
Thank you.
Okay. So now that we trained the RPN, we can extract the regions, and we have the same assignment between regions and ground truth annotations, and we can also train the second stage, and they are all trained simultaneously. One component that we have here is our region of interest pooling, ROI pooling, that actually takes a proposed region in the image space and actually pulls the features that belongs to this one. So we have a proposal and we snap it to the positions in the feature space, and then we apply the second stage on these features.
Describe what is the output of the first stage.
So the RPN outputs for each anchor, whether it's an object or not, and those that are not object, we can ignore them. And for those that are object, it outputs a bounding box where you should look in the image or in the feature space. So now you know where to look in the image space, you know where to look in the feature space, they are aligned. And once you know, you do this ROI pooling, you extract the relevant features from the feature space, and then you can apply the classification and bounding box regression on this and get a prediction for this region. So the second stage can say, okay, you proposed this region, but it's not really a region, it's still a background, I can discard it, but you can say, okay, this is the cat and this is the refined bounding box around the cat.
So the actual bounding box is on the second stage.
Yes. So the output, as a user, the output that you see is the output of the second stage. You don't see what's going on.
Just a comment about the
Yes, yes, David.
When you do this snapping, where do you do the snapping about something like
Interpolation.
Yeah.
Second part. This is accurate enough for detection. It's not accurate enough for segmentation. And again, so this was Roy Pooling and Roy Align actually do the interpolation, and we use later on for segmentation. And interpolation is done by taking a weighted sum of the features around the point that we want to extract. So this is how a bilinear interpolation is done. So we have distance in X and Y, which is a subgrid distance in the grid of features. And we take a sum over the corners based on their distance from the point that we want to extract. So this is just bilinear interpolation. Okay. So this is aligning features, and okay, just a few more minutes and we'll take a break. So during inference, we compute once the features, we run the RPN with all its anchors, it gives us proposals, and for each and every one of the proposal, we pull them from the feature space, and we can predict bounding boxes and classes. But as you can guess, we have a lot of proposals, many of them overlap. So eventually, during inference, we might have this case that there are several anchors that vote for this cat, and they all somewhat overlap. They won't be exactly the same. So as a post-processing during inference, we can apply non-maximal suppression. It's called NMS. So we are going to sort all the predictions we have for a specific class, and each prediction has a confidence score because we predict the probability of that class. And now we can iterate. Once we score all the bounding boxes, we take the most confident one. We are sure this is a cat. We're going to keep this. And all the predictions that have significant overlap with that box, we discard them. So these are the same predictions, but not very accurate. So we can remove them. And now we check if we still have other cat bounding boxes left. These are other cats in the image. We take the maximal one and again suppress those that are significantly overlap with that until we are left with only these confident, non-overlapping predictions.
Question, please.
Yes.
Is there a threshold to the amount of overlapping between the?
Yes, you need to define a threshold. So if you expect objects to be very close by, very overlap, so you are taking a film of a very dense crowd, then you need this overlap to be very small. But if you are expecting to see objects in isolation, then you can be very strict with this overlap. So we talked about the challenge of predicting multiple types of outputs, both classification and regression localization. So we do this by using two heads for the network. And we deal with the varying number of objects by using RPN and this background class. And let's take a break. Let's make it 10 minutes, 5, 10, and we'll continue with some challenges that we might have. Okay, let's continue. So object detection operates very nice. Let's a few things we need to pay attention to. First of all is the imbalance. So the RPN, or the object detector, produces thousands of predictions of possible bounding box. Most of them are going to be background. Only very few are going to be considered as possible objects. So there's a huge imbalance between these two classes. When we trained on the ImageNet, we had roughly the same number of examples for each and every one of the classes. So what's the problem with imbalance? So, okay, so during training, you see a lot of negative examples. During inference, you will also see a lot of examples. So what's the problem with that? So let's consider a case where we have a lot of negative, 1,000 times more than the positive number. What will happen to the cross entropy loss? So I remind you, the cross entropy loss is the prediction 0, 1 times log of the predicted probability.
This is a great way to achieve mathematical.
What? Yeah, so we have a reasonably well working predictor. So most of the background it predicts as background. Only a few of them it makes a mistake and predict them as object. And for those 10 objects box that we have, it predicts one correctly, but it also makes 9 mistakes here as well. So for these, our predictor is very confident. For these, he makes a mistake, but is very unconfident. It's near the decision boundary. So if we compute the loss for this specific case, with this, if we plug in these values, so we'll see that we have loss from these two errors roughly in the order of 10. But from this component that we actually correct on, and we don't need to fix anything, we get a very large contribution that dominates the contribution of these entries that we need to fix. This is because cross entropy doesn't converge. It always tries to be more confident. So it says, okay, I made a mistake here and I'm not confident. That's okay. I was good here, but I can be better. I can be even more confident than 0.99, and I'll gain from this. So this is bad enough, but we don't really care about the value of the loss. What we care about is the gradients, because we are going to fix the system by the gradients of the loss. They will tell us the direction we need to move. So the gradient here are going to be small for those entries that we are trying to fix, but they will be huge for all the other terms that we are correct, because there are so many examples here. So the gradient is going to be dominated by this. So if we want to make a step, it will say, okay, I don't really care about these two. They are tiny. I really want to be more confident about these, which is P. So this is the challenge of imbalance. And you encounter imbalance not only when you train object detectors, you will encounter it in most real-world data sets where you have many negative. If you try to, for instance, classify medical images, most of the patients would be negative, only very few would be positive. And it's very common situation where the data is not balanced. So what are we going to do about this?
What exactly does the imbalance arise in the fact that you have a lot of examples that are correct, right?
So the fact that you are correct doesn't mean the loss is 0. Cross entropy loss never goes to 0. So it always tries to be more confident. So when the loss function looks at this table, it says, okay, one option is I'll try to do my best and improve these few examples I'm wrong on. Okay, I can do that. Or I can be slightly better for these examples that I already good at, but I can be slightly better. I can be 0.999. And because there are so many of these, then I will reduce the loss more significantly if I improve on them rather than fixing those. This is the main problem. So we have a good loss function, but it's not focusing on the right instances. So what are we going to do? One way of doing this is to do hard negative mining. So we can compute the loss in a forward pass for all the anchor points. Most of them are going to be these true negatives. Oh, I can't see them. Very few are going to be these true positives, and we have some false negatives and false positives. Now, naively, what we did before is we compute the loss for all these examples. We'll compute the gradient for all these examples. And then we have this huge imbalance. These are going to dominate the gradient. But we know the loss value, and we know the prediction because we are during training. We have a supervision for these. So we know which examples are here that we are correct on, and we already predict them correctly. So we can simply ignore them. The same way that we ignored anchor points that have this intermediate overlap, so we decided to ignore them. We can drop all these examples from the loss function, and we can compute the loss function only on these very few true positive and true negative that are most challenging for us, that the loss value was highest for them, and include all these examples that we were wrong about them. And now, when we only consider these examples, and we know how to separate them because we have supervision during training, now the loss is balanced because it's a balanced number of examples. And we do it online, so every time we compute the loss, we can reassign examples and say, okay, this example was, I was very correct and very confident about it in the previous iteration, but now I changed the parameters and now I'm not confident. At this iteration, I will include it. It will move to here. I will include it in the loss. Yes?
Can you describe again how we define K for example?
So K is a parameter. This is the number that we want to consider. So we have thousands of anchors that we predicted, and we computed loss for 10,000 anchors, but we only want to consider the 100 most challenging examples.
Now that I understand, but how do you determine which ones are
So we have supervision. So we know how to build this table during training because we know what was the prediction for each anchor and we know what should be the prediction. So we look at all these examples and we say, okay, we don't need to keep all these 9,000 examples. I will only take those that I'm least confident. So I'll take only 9 examples from here. And I'll take these 2 because I'm wrong there. I must compute the loss there. And I'll keep this one because I don't want to forget where I was correct about the positive ones. I can't do this during inference because during inference, I don't know what the prediction should be, but during training, I can do, and loss is computed during training. So we have all the information we need during training, and we can do this adaptively. Another way of dealing with hard negative, with imbalance is to change the loss function. So if cross entropy loss is not good in this case because it tries to improve those that we are confident, we can change the loss function. So this is how the cross entropy look. This is the prediction that we have, the confidence. And if we are predicted correctly for the label, then the loss is low, but it's never zero. And if we are wrong, we predicted very low confidence, although we need to predict this as a positive, then the loss is high. So we see that the cross entropy has non-vanishing loss, so the loss never goes to zero, and also the gradients here are not vanishing. There's also a gradient here. And when we are making wrong prediction, we have relatively weak gradients towards the confident regions. So in this work, what they proposed is a modification. So instead of the cross entropy loss, they proposed the focal loss, which adds this small term, and it amounts to making this curve steeper. So now we have very low loss when we are confident, and the gradient here is also very flat, close to zero. But here, when we are making mistakes, we have very strong gradient. The gradient is much more pronounced than the naive cross entropy loss. Okay, so if we have this hard negative, imbalanced data sets, we can either do hard negative and focus only on the examples that really tells us something new about the data at that specific iteration, or we can actually improve our loss function to handle this case.
Are there any like negatives to using focal loss? What are the positives to cross entropy though?
Let's talk about it later, because I really like this paper. It's really intuitive. In many cases where we had this imbalance case and we used focal loss, it didn't work very well for us in practice. So it's important to know there are cases where it worked, but for some reason it doesn't always work as expected. Another thing is multi-scale. So we want to detect different scales of objects, and these scales can vary significantly. So when we process images in convolutional neural network, we have a trade-off between the resolution of the feature space and the semantic information it contains. So very early on, we have a very high resolution of the feature space because we didn't stride very much, but the receptive field here, again, is very small, relatively small. So the information we have at this layer is mostly about edges, textures, and things like that. And as we go deeper, we have richer semantic information, object parts, some constellations of different components in the image, semantic information, but we lose the resolution. The feature map is very small resolution. So if we want to make different scale predictions, so as we proposed, we can do prediction from different layers of the backbone, but then we need to train different RPN and different localization heads because the features are different, a different dimension, different information. But also we don't have very good semantic information if we are going to too shallow layer. So one way of doing combating this is doing a feature pyramid network where we actually do encoder-decoder kind of network. This is something like UNets that you saw in generation classes, where we actually have one pass that reduces the resolution, and we are continuing to processing the features and increase them, and we have skip connections between corresponding layers. So fine-grained information can travel between similar resolution layers, but the semantics goes from bottom to top and back down. So we end up with feature maps that has both semantic information because they are a result of upsampling these feature maps, but they also pull localized information from the corresponding feature maps. And now we can do prediction on these feature maps that are very rich, both semantically and locally.
You're doing like for each layer in the decoder, like on each layer on the decoder represents a different scale.
Yes. Okay, we really need to go fast. So this was object detection. Can we do better? Set prediction. Okay, this would be in the tutorial. Okay, semantic segmentation. New task. We want to make the prediction per pixel. So we propose, instead of bounding boxes, let's make the prediction for each and every pixel. What is the class of this? So in a single image, we might have cat pixel, dog pixel, duck pixel, and so on and so forth. So we're going to get an image. We have some deep neural network, and it will predict the mask for each pixel. It will predict the probability of this pixel to be one of the classes that we have. So if we have 80 classes, we'll have an 80-dimensional vector for each and every one of the pixels. And we can compute loss with respect to the prediction. But what is the resolution of the prediction of the labels?
Should be the same as the.
It's the same of the image. What is the resolution of the feature maps we have in the network? Far smaller. So we need to bridge this gap. So how do we bridge the gap? So one way is for this task, when we need to make this localized decision, let's not reduce the resolution as we go deeper in the network. Let's ignore the pooling layers. We'll only have layers of convolutions, one on top of the other, until we make a prediction at the same size of the input. So
what about the field of view? We learned that you do that, you don't increase the field of view.
So the receptive field, the field of view, is going to be increased because every time you apply a convolution, you increase the receptive field, but you only increase it by a very little bit. It only increased by 1 or 2 pixels, depending on the filter size. And you're going to end up, even with a very deep network, with a very small receptive field. This is one. And second, processing these huge feature maps is going to be heavy. So what's wrong with small receptive fields? So let's look at this image. And we're looking on a small receptive field. So we are trying to make a prediction based on a very local region in the image. So we're looking at this region, and this is what actually our local network sees. And we're looking at that image region, and this is what it sees. What is the output we expect for these two regions?
First one
Dog and cat.
Second one is clearly a cat.
So this is clearly when you see the image, but if you only see these two boxes, can you clearly see that one is a dog and one is a cat?
They're both dogs.
I would say they are cotton candy.
Yes. So in order to make local, although we are making decisions per pixel, we do want to consider a very large area, the context around these pixels. Otherwise, most of the pixels are ambiguous. So we don't want to work with very small receptive field. So we're going to do a fully convolutional neural network. We are going to apply it in a sliding window classification, but we need somehow to increase the resolution between the feature maps that we have and the prediction. So one way of doing this increase of resolution is doing transposed convolution. So in regular convolution, we have a filter on a dense feature map and it predicts one output. In the transposed convolution, we actually think of spacing the input So we have a 3x3 input space, input feature map, and we conceptually pad it by zeros. So now we have a larger field, larger feature space, and then we apply a convolution, a 3x3 on this spaced feature map. And this spacing allows us to take into account neighboring features, but we predict more features. So in a convolution, we usually have, we discard the boundaries, unless we do padding, and we have roughly the same size. When we do transposed convolution, depending how much we space between the features, we can actually get a larger output with respect to the input. So in this case, it's a 3x3 and a single spacing, and we get a 5x5 output. And we can do this drastically and increase the resolution of the feature map with these transposed convolutions. So we can process the image with a trained backbone, and we can fine-tune it. And then we can apply this transposed convolution and increase the resolution of the prediction to the resolution of the predictor of the image. And you can guess that there's a trade-off between how much we downsample and how much we upsample in this layer. So this can't really compensate for all the missing details that we have. And the fully convolutional network paper actually did this trade-off for us. So they trained several flavors, one with stride 32, which actually means that we drastically reduce the feature map and expand it. So you can see that it gets these blobs where the objects are, but no details at all. And if you do only stride 8, you are able to recover finer details. So we want to do striding in order to increase the receptive field, and we pay for this because we need to recover the feature, the resolution. Another way of increasing the receptive field without striding is actually spacing the convolution filter. So this is a 1D convolution. So for the kernel size of K, we have the kernel filter and we apply it on the image, but we have a spacing parameter here. So we don't have to apply a 3x3 filter on a 3x3 neighborhood in the image. We can actually space it. So now the filter is a 3x3. We are learning the same number of parameters, but the receptive field is larger because we space it. And this is actually equivalent to pulling and applying the 3x3 on the pulled feature space, but we are doing it for all the features. So if we have an image, we do a pulling and a 3x3 and then upsampling, we see that we have this aliased feature map. But if we apply the same filter with this spacing, we get the same resolution of feature map, but without the aliasing, because we actually applied it on all the pixels. So we didn't sample and upsample, we only applied it with a spaced feature map. And this work, Deep Lab, actually proposed to use a stack of filters with different kind of spacing, which actually accounts for different sizes of receptive field. And they are actually able to do segmentation without this drastic decrease and increase in the receptive field. The cost of it, of course, is that you pay with denser feature maps because you didn't sample, but the trade-off in computation is reasonable. As you can see, you can recover detailed minute of details of the segmentation masks.
isn't the attention better suited for this sort of task? Like which pixel is relevant to?
So the problem with attention is that you can't work with very large images because you're limited by the number of tokens you can process. So there are variations that allows you to do efficient attention on images, and then you can use these backbones for these dense predictions. You need to take into account the size of the token. So if you are doing a 16 by 16 tokens, you already decrease the resolution by a factor of 16. So using this space, this or dilated convolutions, we can trade the striding and pulling with this spacing of the kernel. We increase the receptive field without increasing the number of parameters. We pay in a computation because we have larger, denser feature maps. Another way of solving this trade-off is like we saw earlier in this class with this feature pyramid network. In this context of segmentation, it is called UNet, and it's a very popular architectural concept for dense prediction. It is used also for generation of images. So the backbone in diffusion models is usually a variation of a UNet. Again, more modern one with attention layers as well. This basic version was before attention. So we have an encoder that gets high resolution image, very few number of channels, and as it processes it with striding, it increases the number of channels, increases the semantic information, but reduces the resolution. And then we don't do upsampling at a single stage. We do it gradually. And we have skip connections that passes high resolution information from the corresponding layers. And we end up, like in the feature pyramid network, with the features that have both semantic information as well as details that they pulled from the corresponding layer. Okay? So the main challenge in semantic segmentation is this trade-off between resolution and semantic information. And we saw several ways of dealing with this, either by doing this transposed convolution, or by dilated convolution, and instead of transposed convolution, we simply interpolate, or using this UNet with skip connections.
Units works the best, yeah. The best performance.
Depending on the task, I think deep lab with dilated convolutions also performs quite well. It really depends on the task, but so I guess the first approach with like a single stage is like the most naive, and really it's fast but not very good. The other two, I guess, whatever task you are, whatever architecture you decide, you'll make it work. So there's a slight trade-off between computation resource and resolution in both. Last but not least, we want to do instance segmentation. So now we don't want to make a prediction per pixel for each class it is, but also we want to differentiate between pixels of the same class belonging to different instances of the same object. So these are going to be dog pixels, and it's very easy to segment them. We don't need to do anything special in that particular image. But for the cat pixels, we have nearby pixels that look the same. They both have the same semantic meaning. They are both cat, but we want to separate them because the left pixels belong to one instance of the cat and the other to the second one. So how are we going to approach this problem.
We have tag data. I mean, we have.
Yes, we have. We have annotated data. The data is annotated per instance. Everything is supervised. We are at the very basic. We are not trying to complicate this thing. But in terms of the design of the system, the network, how are we going to make this kind of predictions?
So different label for every
But again, okay, in the data, this was cat 1000 and this was cat 1001. Now I'm going to give you a different image with two cats. What's going to be their labels? 1000, 1001, or cat 6 and cat 83? You're going to label all the cats in the world. There are quite a few of them. And if you have ants in your lab, are you going to tag all the ants?
Just don't take pictures of new cats.
Maybe we can use classical methods like watershed.
So we're going to combine ideas. So first of all, we have the data. MS Coco actually provides annotations per instance. And we're going to combine these two things that we learned. We're going to combine object detection and instance segmentation. So we're going to present mask RCNN, and we're going to do this very briefly. So we have an image. We have a region proposal network that actually crops different objects in the image, different instances of objects in the image, because this is what it was trained on. But now we can add a third prediction head for each box and do a semantic segmentation within that region. Because in each region, we only have one instance of the object. So we can apply the instance segmentation methods that we learned. So we can take whatever network that you want, a small unit or whatever, and it already has these rich features. So we can apply very small network to predict the mask here. And the output would be for each bounding box, the mask for that specific instance. And then we can do non-maximal suppression and so on and so forth. And we end up with these kind of predictions. Again, 2017, this was very impressive. That you actually have bounding boxes and exact mask for each and every one of the instances of the object. So if you have two cats, you'll have two bounding boxes, and you'll have a mask for each of the bounding box for the cat that is dominant in that specific box. Yes.
When you have the bounding box, you're you're interpolating it back because it's smaller. It's on the feature space, and
Yes.
So how do you map the pixels?
So you have the positions of the bounding box, so you have the position of the predicted mask. So you can map it to the image. If you know the architecture of the backbone, what is the stride and what are the padding that you used in the computation of the backbone, you can actually map each position in the feature map to the corresponding position in the image and vice versa. So each XY position can be mapped. We actually thought of giving you this as an exercise, but exercise 4 wasn't applied this semester. So, yay! But you can do it as an exercise if you want.
So, can I repeat my question from earlier?
Yes.
So I would say it's the opposite. If I have the pixel, if I have the instance segmentation per pixel, now the bounding box becomes almost instantaneous. Just just the bounding box of the pixels that belong to that animal or instance or whatever.
Yes, but you need, of course. So if you want only the bounding boxes, then you don't need to do the instance segmentation. But if you want to separate instances, you need the bounding boxes in order to separate them. So otherwise, you have a blob of cats, and you don't know how many cats are there. So if you work in a domain where you know roughly the shape and the size of objects, or for instance, you work with cells on a Petri dish, and you roughly know what is the size of a cells, and you want to count them, then you don't need to do instance segmentation. You can actually do semantic segmentation and divide by the number of pixels, the average number of pixels per cell. Then you get a count, a good estimate of the number of cells without actually going through the separation of the cells. But usually if you want to separate the object, you need to go through this separation and then the segmentation. Otherwise, you're stuck with blobs of semantic regions, and you don't know how many objects there are in that regions.
So is there some unsupervised way of doing these sorts of tasks?
I guess there are. I'm not familiar with out of the top of my head.
How exactly you find the contour of like between the categories? You find in the bounding box, you have the.
So you have a bounding box of a cat, and you have the supervision of the mask for that specific cat. So during training, so you have one cat, and you have the second one, and then you have this bounding box.
Yes.
So the supervision for this mask head for this region is going to be only this. You will predict 0 here and 0 here.
In the training, you already got it. Yeah.
During training, you have the masks for each and every one of the instances. So these are all sheets, but someone painfully annotated each and every one of them. Yes, pain in the sheet. But luckily you have the data. So, but if you want to do this for ants, then good luck.
Can you go back one slide?
Yeah, well, I think I can. But we really need to conclude. So I'll conclude and then you'll ask questions. So this is mask-RCNN. So to conclude, we saw this in this class, taking deep learning beyond the task of classification generation to more complicated and more detailed predictions in the image space. We used a backbone. We take it from image classification backbone. So we do transfer learning rather than training from scratch. We use the same features for the classification and the localization. So the features are very rich. They hold this information. So we multitask. And actually this multitasking improves the features. So if you have many different tasks, train them on the same features. Usually it's the same information that you need for all the tasks. And we saw how we can handle varying number of predictions by predicting this background label that we added. And we can cope with different sizes of receptive field and resolution, either by transposed convolution, dilated convolutions, or these skip connections. And for next week, which will be the last week of the semester, on Monday, Rafael will teach you about models that combine text and image. And on Wednesday, Leo will give you the second part of detection segmentation. I think it will cover YOLO and some other modern aspect that takes into account concept from transformers as well into these tasks. Okay, we'll conclude now, and if you have any more questions, we'll take them. Thank you very much.